Somewhere outside Phoenix, or maybe in a cold river valley in the Pacific Northwest, there's a building the size of a small town. Server racks run in tight rows for hundreds of meters. Cooling systems blast non-stop, fighting heat thrown off by thousands of processors running flat out. One of these places alone can pull as much power as a mid-sized city, and it basically never shuts off, because on the other side of some screen, somebody's asking an AI to write an email, or read a scan, or plan a business strategy. That's the physical reality behind modern AI. Not a sleek algorithm floating in the cloud. An enormous, expensive, power-hungry machine that keeps needing to get bigger every year. For a few years now, there's been a fear going around tech circles and boardrooms and news headlines. Quantum computing is coming. It'll hit like a storm, and it'll make everything we've built obsolete and force a total rebuild. I think that's mostly the wrong story, and so do most of the people actually building these systems. What's happening inside serious engineering labs right now isn't about replacement. It's integration. What becomes possible once quantum computing stops being a threat sitting outside AI infrastructure and starts moving into the middle of it? So here's a better question than the one the headlines keep asking. What if quantum computing isn't the threat AI data centers are bracing for, but the fix for the problems already quietly tearing them apart? Start with what's straining right now. Scattered around the world is a sprawling network of data centers that quietly run modern AI. These aren't small rooms with blinking lights. They're industrial operations. Walk through one and you'll see row after row of GPUs, originally built to render video game graphics, now doing the heavy lifting for machine learning. They run constantly, trillions of calculations a second. That's what lets an AI spit out a photorealistic image in seconds, or hold a conversation across dozens of exchanges, or find patterns in datasets too big for any person to process. It comes at a real cost, though. A single large data center can use as much electricity as 100,000 homes. The heat is so intense that cooling systems run non-stop just to keep the hardware from melting. In some facilities, the fan noise is louder than a jet at takeoff. And it keeps getting worse. Models don't stay the same size. Every generation is bigger and more expensive to run. GPT-3 had 175 billion parameters. GPT-4 is rumoured to be a lot bigger. Whatever's coming next is expected to cross into the trillions. Every jump in capability needs an even bigger jump in compute underneath it. Meanwhile, the hardware is hitting physical walls. Chips can only shrink so far before quantum effects at the atomic level start causing errors on their own. Some power grids genuinely can't keep up with demand. Heat removal is becoming its own crisis. There's only so much thermal energy you can pull out of a tightly packed machine without redesigning the whole thing. There's also a quieter problem engineers call the memory wall, the gap between how fast a chip can compute and how fast it can fetch the data it needs. Picture someone brilliant stuck working 3 floors away from every file they need. Doesn't matter how fast they think. They spend all day walking back and forth. That's the actual bottleneck inside AI hardware. Not thinking, waiting. Companies are spending hundreds of billions trying to engineer around this. Better chips, better software, more data centers. It helps a little, but the gains are incremental and the problems are exponential. And at some point, you just can't keep building more of the same thing. This is where quantum computing actually shows up. And it's worth being precise about what that means, because the term gets used loosely. A classical computer, your phone, your laptop, every server in every data center, runs on bits. 0 or 1, off or on, long chains of binary steps run one after another. It's extraordinarily powerful. It's also fundamentally linear. Solving a maze, it checks one path, then another, until it finds the exit. A quantum computer works differently. Instead of bits, it uses qubits, and thanks to a property called superposition, a qubit can be 0, 1, or some mix of both, until it's actually measured. That's not magic, it's physics. It means a quantum processor can explore a lot of possibilities at once instead of one at a time. Same maze, but it's checking many paths simultaneously. That doesn't make it faster at everything. It won't load your email quicker or stream video smoother. Quantum hardware is built for a narrow set of problems. Heavy complexity, probabilistic reasoning, optimization across huge solution spaces, simulating systems classical computers struggle with. And those happen to be exactly the problems straining AI infrastructure right now. Training a large model is, underneath it all, an optimization problem, searching billions of possible parameter combinations for the ones that fit the data best. Right now, that search is brute force. Burn electricity, burn time. Because classical hardware has no shortcut. A quantum processor built for optimization could shrink that search dramatically, at least on paper. Then there's simulation. Molecular interactions, atomic-level material behavior, how biological systems respond to drugs. These are quantum mechanical problems by nature. Classical computers only approximate them. Quantum computers can model them directly. For AI working in drug discovery or materials science, that's not a small upgrade. And none of this is hypothetical anymore. In December 2023, Google's Willow chip showed that error rates can actually drop as you add more qubits. A real reversal of a problem that's dogged the field for years. IBM has a public roadmap toward fault-tolerant systems by the end of the decade. Microsoft is betting on topological qubits, a design meant to be more inherently stable. Maybe the clearest sign of where this is headed isn't happening in a lab at all. AWS, Google Cloud, and Microsoft Azure, the platforms running most of the world's AI workloads already, now rent out quantum processing time the same way they rent GPU clusters. You can book quantum time like you'd book a server. The hybrid setup isn't a pitch deck anymore. It's already running. Not quantum instead of classical. Quantum next to classical, picking up the jobs classical chips are bad at, while classical hardware keeps doing everything else. That's not some far-off possibility. It's being deployed right now. So what does this actually change? Drug discovery is the most obvious case. AI already predicts protein folding, finds promising drug candidates, simulates how molecules interact with biological systems. It's already turned years of research into months. But there's a ceiling. Classical computers can only approximate the quantum mechanical behavior of molecules. They can't simulate it directly, and the complexity grows exponentially with every atom you add. For big, complicated molecules, the kind relevant to cancer, Alzheimer's, drug-resistant infections, that approximation starts to fall apart. A quantum computer doesn't approximate quantum mechanics. It runs on the same rules. Paired with AI trained to interpret and optimize the results, quantum simulation could remove that ceiling entirely. A decade of pharmaceutical research could, in theory, collapse into a few years. Maybe less. Material science has a similar shape. Better batteries, more efficient solar cells, superconductors that work at higher temperatures. All of it depends on understanding atomic and molecular behavior, which is again a quantum mechanical problem. Classical AI can suggest candidates. Quantum AI systems could actually simulate them with an accuracy no classical machine can reach. Finance might move faster than people expect, honestly. Markets are absurdly complex. Millions of interdependent variables shifting in real time. And quantum optimization could let risk analysis run at a scale classical systems just can't reach. This isn't science fiction. Banks and hedge funds are already testing quantum algorithms. The question isn't whether this becomes part of financial infrastructure. It's when. National security is the part people talk around in public, but think about constantly in private. Yes, quantum computing could eventually threaten current encryption. That's real, though not an active crisis right now. Current encryption still holds. But the bigger story is quantum secured AI as a strategic advantage. Whoever can model complex systems, run scenarios and process intelligence faster than an adversary has a real edge, not a marginal one. And then there's the most boring, most immediate piece: power. AI data centers are already straining electrical grids. Some proposed facilities have been delayed or blocked outright because local utilities can't supply enough electricity. If quantum processors can take over the most expensive computational tasks, optimization, simulation, search, the energy savings could be enormous, not someday. Within years. This isn't one single breakthrough. It's a bunch of overlapping possibilities across healthcare, energy, finance, security, infrastructure. Some of it's close, some of it's a long way out. A few pieces are still pure speculation. But the direction keeps getting clearer. None of it's going to arrive smoothly, though, and it's worth saying that plainly. The potential is real, the momentum is real, the money being spent is real. but so are the obstacles, and skipping past them would be dishonest. The biggest problem is exactly where it's always been. Quantum computers, even the best ones being built right now, are extraordinarily fragile. A qubit isn't like a transistor. It sits in a delicate quantum state that can get knocked over by almost anything. A slight vibration, a temperature fluctuation, stray electromagnetic noise from some nearby device. Any of it can cause decoherence. The state collapses, and errors creep into the calculation. That's why these machines run in heavily shielded rooms, cooled close to absolute zero, isolated from outside interference as much as physically possible. And even then, they error out. Often. Error correction is improving. Willow showed errors can actually drop as you add more qubits, which reverses a trend that's haunted the field for years, and that's a genuine milestone. IBM and Microsoft are making similar progress. But fault-tolerant quantum computing, systems that run long, complicated calculations reliably without constant correction, is still an enormously hard engineering problem. It's being worked on. It isn't solved. So when does this actually happen? Honestly, it depends who you ask. Most people working directly in the field put practically useful, large-scale quantum AI integration somewhere between 5 and 15 years out, depending on the application. Some think narrow quantum optimization wins land sooner. Others think the hardest stuff, full molecular simulation tied seamlessly into AI drug discovery, takes a lot longer. The range is wide because nobody's faking certainty here. The uncertainty is real. There's also a geopolitical layer that shapes how fast any of this actually moves. The US, China, and the EU are all pouring billions into quantum research, and not just as a business bet. Governments are treating it as a national security and sovereignty issue. China's built national quantum labs and launched quantum communication satellites. The US has passed legislation specifically funding quantum development. The EU has folded it into its digital strategy as a strategic priority. None of this is happening in a vacuum. It's tangled up in a much bigger contest over who controls the infrastructure that defines the next stretch of technology. And not everyone buys that the hybrid model will work as smoothly as its boosters claim. Some researchers think the engineering challenge of connecting quantum processors to classical AI systems at the speed and scale required is being underestimated. Moving data between the two, managing coherence times, syncing fundamentally different architectures. None of that is trivial. These researchers aren't dismissing quantum computing. They're just skeptical the integration will be as seamless, or arrive as fast as the optimists assume. That's a fair concern, and it deserves to stay in the conversation rather than get waved off. What people in the field are actually watching closely over the next 2 or 3 years comes down to 3 things. Whether the error correction progress Willow showed can be repeated and scaled up, whether the number of stable, usable qubits grows fast enough to handle real problems instead of lab benchmarks, and, the one that matters most, whether anyone demonstrates real quantum advantage on an actual AI task, not a theoretical proof, an actual task on actual hardware, beating classical systems at something real. That hasn't happened yet, but the distance to it keeps shrinking. So, back to that building outside Phoenix. The servers stretching past sight, the constant hum of cooling systems fighting heat, the electricity bill rivaling a city's, the physical infrastructure quietly running the AI tools billions of people now use without thinking twice, diagnosing disease, managing supply chains, writing code, answering questions no one person could answer alone. For a while, the dominant story was that all of this was fragile, that quantum computing would show up like a storm and make it obsolete, that infrastructure built at enormous cost would need tearing down and replacing with something else entirely. I don't think that was ever the right story. The real question was never whether quantum computing would destroy this world. It was whether it could make it better, more powerful, more efficient, capable of solving problems we can't even approach right now, and sustainable in a way today's infrastructure, no matter how optimized, just isn't. Big technological shifts don't usually work by replacement. Electricity didn't get rid of mechanical systems. It made them more capable. The internet didn't tear out the phone network. It rewired it from the inside. Quantum computing looks like it's heading the same direction. Not demolishing AI data centers, but moving inside them and picking up the work classical processors are bad at. And this isn't some far-off abstraction anymore. Cloud platforms already offer quantum time next to classical compute. Labs are showing error correction results that make real scaling look plausible. Governments and companies are funding actual engineering now, not just speculation. It's happening quietly, while a lot of people are still arguing about whether quantum computing is even real. It's real, and it's starting to merge with the technology we already depend on. I keep coming back to one question. When a genuinely hybrid quantum AI data center comes online, and most people working on this think it will, within a decade, what becomes solvable that isn't right now? What disease research speeds up? What materials get found? I don't have firm answers, and honestly nobody does yet. But it feels less like speculation than it did even a couple years ago.